take care of all of that. Okay, I think now we are live and you can start again, Ria. Sorry about that.
Don't worry. So I'm just going to get right into my presentation. My presentation was about analyzing the transit of planet HD 189733b, and I participated in this program with two other people, and I'm just going to be going over exactly what we did. So for some background, so being in the astrophysics track at SRA, we had access to telescopes from the Las Cumbres Observatory, and we specifically used the 0.4 meter ones. So here is a map of the Las Cumbres Observatory, and you can see that there's a lot of locations, for example, in Texas and Hawaii and Chile. And this was really good for us because it allowed us to observe planets and galaxies, etc., that weren't directly in our night sky. So we had a wider range of observation. So we first had to decide what exactly we wanted to observe. SRA and my mentor gave us the option to observe binary stars or galaxies or exoplanets, and me and my group decided that we wanted to observe exoplanets because we thought it'd be a lot more interesting and we could get some interesting light curves and results. So I'm just going to kind of go over some more background. So observing an exoplanet that's transiting in front of a star can reveal a lot of things. So this GIF over here shows how the apparent brightness of an exoplanet of a star shifts during a transit. So when the planet is in front of the star, light is being blocked. The light that we observe is being blocked. So when we observe this light, we can see that there's an apparent dip in this light. And this dip, this change in brightness, as we can see here from the top and the bottom, this is something called the transit depth. And this is the ratio of the surface area that the planet blocks from the star. So using this ratio and some other equations, we can estimate the radius of this planet, which is exactly what me and my group did in our project. So I'll now move on to methods, and I'll just be talking about the code and some of the equations and stuff that we used. So the first star that we actually ended up observing didn't end up being the final one in our project, but it did provide a lot of useful insight into telescope observation. So in this picture, this bright star over here that I'm circling is WASP 46, and we observed this using 3 filters, the GP, RP, and UP filter. So all different filters in the telescope capture different types of light because stars emit different types of light. And the GP filter collects green, the RP collects red, and the UP collects ultraviolet light. So the results that we get from the Las Cumbres Observatory telescopes come as a set of FITS files. And this is a digital file format that's commonly used in astronomy. And each image is basically an array of pixels where the color of each pixel corresponds to the brightness of an area. Like, for example, because this pixel is colored white, we know this is a very bright area, while the rest of the background is pretty dark, which means it's the black area in the night sky. And using Python code, we converted these files into images. So this isn't what the file initially looked like. It had to be converted. And we converted it into images like this one. But in the end, we concluded that the star just wasn't bright enough for our observations. So at LCO, we were only allotted a certain amount of time. And to get a bright and clear image like this one, it was just taking too long because the star wasn't bright enough. And the more dim a star is, the more time it takes to collect ample amount of light to make it bright in a picture. So we concluded that we needed to find another star and planet to observe. And this is where we found the HD 189733 system. So a little bit of background about this system. This contains of 2 stars, which I'm just going to call HDA and the other star because the other star is really far away. And this is a binary star system. So HDA is a bigger, almost sun-like star, and the dimmer star orbits it every 3,200 years. And the planet, which I'll just call HDB, it's a Jupiter-like star, and it orbits its parent star around every 2 days. And using SIMBAD, which is an astronomical database, we concluded that the magnitude of HDA was a lot brighter than WASP 46. So we thought it would be better to explore. and the 2-day transit period meant that we would be able to observe it quite often throughout the course of our project. So this picture over here is a artist rendition of the HD star system, and the blue object over here is the planet. So here's a timeline of the different observations that we made. So the first observation that we made was WASP 46, which I showed you guys before, and that we made on July 7th. That was just one picture. And then we made another observation on July 11th, and this was of the HD system. And then we made our last and final observation on July 15th. So we took around 132 images on the July 11th observations. And then we took about 300-ish more on the 15th observation. So this is what we got after we observed the star, after we observed the HDA. So this specific image is from our July 11th observation, and the star circled in the middle is HDA. And like I said, we took around 430 images over the 2 star observations. But with these images, we still have to find the change in brightness. This is just the image that's showing us where the star is. How do we do that? We used a technique called aperture photometry. So this technique is basically where you sum up the light in a given aperture. So for example, in this picture, we can see that the star is surrounded by the smaller ring, and aperture photometry is just summing up the pixel values of that ring. You want your aperture to be small enough to encompass the entire star, but you don't want to get the background light in it, because as you can see here, the background itself isn't completely black, it isn't completely dark, it does have some sort of magnitude. So we have to account for that while we're conducting aperture photometry, and we want to subtract that while we're calculating our final magnitude. So if we perform aperture photometry and we calculate the magnitude of a star in an image, and we do that on all of our 400 images, we will basically get a light curve if we plot that against time, and we can see how the magnitude has shifted over the transit. Another important aspect of my project was a standard star comparison. So we want to make sure that the change in brightness that we observe is actually coming from the star instead of other sources, like some light being blocked or something else. And to do so, we use something called standard star comparison. So basically, the star that we're observing, HDA, is a variable star. That means its magnitude, its apparent magnitude from Earth, varies because, well, in this case, it has a transiting planet, but a variable star can be any star that has a changing magnitude over time, compared to standard stars, which don't have a changing magnitude. So we wanted to compare the magnitude to a standard star instead of just observing the magnitude alone, because if the magnitudes vary for a reason, they'll all vary with the same or close to the same percentage. So it'll be a relative change rather than a change overall. So that just reduces error, and it'll make our calculations a lot more accurate. So the next part of my project was to do the standard star comparison, we used a lot of code. So we had to find all the bright stars in the code to figure out the ones that we had to use. And we used a lot of special Python packages like AstroPy, NumPy, Matplotlib, and Phototils. So this image represents one of the packages at work, and it's finding and circling all of the bright stars in the image in red. So the star in the middle is HDA, and we want to find 2 other stars that were bright enough where we could perform the standard star comparison. And we looked in SIMBAD, which I mentioned earlier. So SIMBAD gives a lot of information about stars, and it provides like a 2D view of star fields all around, like in the night sky. So we zoomed in on the star field around HDA, and we found 2 relatively bright standard stars, and we used those for our standard star comparison. So these are those 2 stars. This star over here is around here in the field, and this star over here is around here. So we use these 3 stars overall to make to find the relative magnitude of our project. And so to derive an accurate value for the relative brightness of HDA, we calculated and then we subtracted the value of the brightness of the reference star from the brightness of HDA. So we got the relative magnitude. we also took into account the brightness of the stars and the brightness of the sky and the surrounding stars. And we also subtracted this from our calculation, and we processed a lot of the errors along the way. So to calculate this brightness, we needed an aperture size that captures all of the light that's emitted from the stars. And we basically zoomed into this picture and saw the width of the star, and we said that it's around 20 pixels. So that was the aperture size that we used for aperture photometry, and that worked out pretty well for the rest of the stars. So here is the magnitude versus time graph for our July 11th observations. And in this observation, instead of observing the transit as a whole, we set up 3 different observing periods because we wanted to observe it in and out of transit. So this first observation over here is the planet out of transit, and this is its normal relative magnitude, versus the clear dip here is the relative magnitude while it's in transit. And while this was a good initial start, like we definitely saw a dip, we wanted a clear picture. Like it would be really good if we had a clear curve. So we thought we could do better, and that's why we set up another observation on July 15th to observe the star in full transit. And this time we set up we set up a full transit period. We set up our observations during the full transit period, so we would capture we would just capture images from all parts of the transit and create a clearer curve. And this is our final light curve from our July 15th observations. So it's a lot better than the one we had before, obviously, and it's a lot smoother, as we can see a clear dip and a clear rise. And this was really exciting for us because we didn't expect our results to be this good. And basically each of these points over here is one of the magnitudes that we measured, and the bars up and down represent an error bar. So what this light curve tells us, this is basically the results portion of our project. So the orange line on top is the line of best fit for the relative magnitude outside of transit. And the blue line over here, I know it's kind of hard to see, is the line of best fit for the planet in transit. So we needed these values because we had to subtract it. We had to subtract this value from this one to find the change in brightness, which we needed to find the radius. But basically we concluded the change in brightness was negative 0.02881, 881, and that was just a change in brightness. And to figure out the transit depth, which we again need to find the radius, we had to normalize this curve, and this is the value that we got for our transit depth. So to figure out the radius, the transit depth that we calculated earlier is directly tied to the radius of the planet, and it's through this equation where we get transit depth. Also we can denote it using delta. This is equal to the ratio of the radii of the planet and the star squared. So we know what the radius of the star is, and we just calculated our transit depth. So we can calculate the radius of the planet, and we concluded that to be around 1.3 Jupiter radii, and we put it in Jupiter radii just to make a comparison to something that we're already familiar with. So, there's a slide. I think I'm missing a slide. I'm so sorry, but I want to talk about some sources of error. I'll just go over to this slide. So a source of error for us could be like imperfect viewing conditions. Although we tried to correct for that using our standard star comparison, there still could have been like something blocking our view, and that could have led to imperfect observations. And another source of error could have been the way we define our in transit versus out of transit. So we defined in transit to be from around 0.6 to 1.4, and out of transit to be from 0 to 0.3, and then around 1.7 to 2.1. But we could have easily shifted these values around by like a few points. So this could have been like 0.8 to 1.6, and that could have skewed our line of best fit, which would then change our value for the change in brightness and the transit depth, and that could have possibly affected our calculations. And for further research, I think it would be really interesting if we observed this transit in different filters because we only observed in the blue filter. So something about observing it in different filters is that different filters let different light pass through, and you can actually use this to find atmospheres on planets, because if you're observing through a certain filter, you can see if the radius that you calculate is bigger than the radius you calculate in a different filter, and that would be because you would be observing the atmosphere as well, because like one filter would be letting that light pass through and one filter wouldn't. So that would tell you a lot about the composition of the planet if you can figure out which light would be passing through or not. And I also wanted to share my code that I used. So unfortunately, I had to get my laptop replaced because my old one shut down, and almost all of the code that I had on it was on it, and I wasn't able to recover it. But I do have one of our preliminary files that I uploaded onto GitHub. So I'm just going to be like going over that and showing you all the stuff that I was talking about. So so the first part of this is just us opening the FITS file. Like I said, the images that we got from LCO came in the set of FITS files, and when we use this first part of the code to just open it, and just to make sure that our image was looking good and we could actually use it for observations. So the next part of the code is us trying to find all the bright stars in the image, and we set it so that it would we defined a bright star as something that would have a pixel width exceeding 5 pixels and some other parameters. So once it did that, we again used, and this also used an algorithm called the DAO star finder, which is really helpful because this is basically what just found all the stars in the image. And after that, again, we went to Simbad and we concluded that we would want to use, I think it was this and this star that we would use for our standard star comparison. So the next part is basically we wanted to count the amount of stars in this image above, and this is just some code that just enumerated the stars. This is just some extra stuff that I calculated that we didn't need until later. So this is where we're actually finding the aperture sum. So the aperture sum and the magnitude that we calculated are different. You use aperture sum to then calculate magnitude, but this is basically the code just counting up all of the pixel values in this circle. So for example, for this one, it was just counting up everything in here, and it was putting it in a list. So we also then sorted this list to make sure that we were using the right star, because our star HDA was the brightest star in the field. So we wanted to make sure that we were actually using this star, which has the largest aperture sum, and therefore it's the brightest star in the field, and it's the star we want to use. So this next part is the standard star comparison, and it's basically we just listed the 2 stars that we wanted to use, and in our case it was this TIC 1508 and TIC 916, and we calculated their magnitudes and subtracted that from our we calculated their aperture sum and subtracted that from the aperture sum of HDA. And yeah, this is just listing, and this is just converting it into magnitude. So we use this equation over here to convert all of the data that we have into magnitudes, and then we just get a list of this. So this part is basically just combining everything that we did above into functions, and yeah, it's making it a lot more concise. And in the end, after we perform aperture photometry on every single image, so this code basically runs through 400 plus images to create the graph, but that was just for one image that I showed you. So after all of that, we get a list of magnitudes, and if we just plot that, this is where we get our light curve. Not shown here is the line of best fit stuff that we did, because again, I don't have those files. But yeah, that's pretty much my project. Thank you guys for listening.
Thank you, Ria. Well, that was a great presentation. I'm just checking in the YouTube chat channel if anybody has any questions there, or the floor is open for Q&A here. You can either unmute yourself, and I had to mute a couple of you during her talk because I was getting some echo. But feel free to unmute yourself now and ask your question or type it in chat and I can relay it on to Ria. Whatever works for you.
I'm trying to remember, there was a guy at Santa Cruz who came to the SJAA meeting one time and talked to us about amateurs trying to get light curves like this. I don't know how many people picked up on that. This had to be more than 10 years ago, I guess, because I was still working on a master's at that time. And so this was a great presentation of what can be done. This done by high school students just kind of blows me away, in fact.
Thank you.
It was really great.
Thanks, Paul.
Yeah, it was really fun. It was actually pretty interesting because I was really concerned that because my project was remote, because this was all remote over COVID, that like it wouldn't be as fun, but just seeing how much we could just do from our laptops and just code, it was very interesting. And I'm like really glad with how my project turned out.
That's great.
Ria, this is Swami. I have a question for you. How did you go about finding about this opportunity at UC Santa Barbara? Was this through your school or did you use some other avenues to explore possible opportunities for high school students to get involved in such projects?
So I was actually, during my junior year, I was doing a lot of research about summer programs that I could do. And I just came across this one because I got an email from UCSB. They actually have two programs. One is the Summer Research Academies and one is the Research Mentorship Program. And I just like this one better. And this actually had astrophysics, so I applied to this one. But I think there's actually a lot of summer programs and stuff like that that students can apply to, and UCSB has like really good programs. So yeah, there's a lot of like online resources that I used.
Okay, so this was not through your school. This was just you personally, you're
Yeah.
independently looking for opportunities.
Yeah.
All right, thank you.
That's great. And then Stefano is saying, thank you, Ria, for a great presentation of your great work. What is your next project?
I think the next project that I do will probably have to be in college because I am graduating soon, and I'm really hoping that I get some research opportunities wherever I go. And thanks to like some research experience that I already have, I hope like I'll do some more interesting stuff.
That's great. Do you know where you're going to college?
Not yet. Results are still coming out.
Oh, you're just entering the senior year, or just?
No. I'm graduating this year, but all of the college like acceptances haven't come out yet, so I'm still like not sure where I'm going.
Okay. Well, are you hoping to do research in astrophysics or any?
Yeah.
Okay.
Yeah, pretty much astrophysics. Yeah, that's kind of, I want to pursue astrophysics and data science in college, so I'm hoping I get some research opportunities.
That's pretty cool. Good luck with that.
Thank you.
Paul just shared an interesting article in chat if anyone is interested. Gregory Lawlin. Yeah, that doesn't ring a bell. It's definitely a while ago, before my time at SJAA maybe. Well, let's see. Any other questions? Maybe you covered this, but I'm just curious, why did you select this particular star to study?
So we kind of looked up like planets with transiting stars in front of it. Oh, sorry, stars with transiting planets in front of it. And we had a few resources of what we wanted to observe. And like we tried a couple of stars, like we tried WASP 46, and we just concluded that that wasn't bright enough. So we went back to our research and we found this star, and we did a test observation and it went pretty good. So we just continued observing this star. So it was kind of just by luck that we chose this specific star because it fit all our parameters. Like the transit period wasn't that long where it took too long to observe. And the magnitude was pretty bright compared to the other one that we observed. So it just, yeah, that just happened kind of by chance.
And did you have to learn any new coding skills to do this project, or
yeah, a lot
Python?
of this, yeah, well, I knew like basic Python before this, but a lot of the like astronomy specific stuff, like this was all pretty new to me. Like I'd worked with like Matplotlib, but I hadn't worked with like AstroPy, and it was really interesting to see. It was really interesting to work with like all of these different Python like packages, and yeah, so I definitely learned a lot of new coding skills in this project.
Cool. One more question coming in from Stefano. Ria, can you please explain a little more why you need to use the dot fits format?
Yeah, sure. So basically, that wasn't something that we like had a choice in. Basically, the Las Cumbres Observatory, when it observes stars, it automatically captures images in the dot fits format. So when we were observing from here, we just had to take the file and go. But I'm pretty sure it's a pretty commonly used like astronomical like type of file, because like, okay, let me scroll up. So I think files like .fits encode a lot of astronomical data that you wouldn't be able to get from a regular image. Like for example, the only reason we were able to use, for example, the DAO star finder is because the file wasn't a fits file and it could like find the stars. So I think it's just a standard like astronomy image file that's being used. Yeah.
Okay. Let's see. I'm just checking one more time. Somebody is trying to say something, maybe? I saw some unmute happening. Richard is saying, I hope you're able to recover your full code. Make sure you keep that hard drive.
Yeah, I had everything saved to my laptop and I didn't upload it into GitHub, which was a mistake, but I've learned that mistake and I will not be doing that again. It was so unexpected. My laptop just completely crashed while it was updating and I like wasn't able to recover anything, but yeah, I've learned from that. Now I just upload everything onto GitHub.
Yeah, we don't rely on hard drives anymore, do we?
Well, even if the laptop crashed, the drive itself may still be okay, right? So you may be able to recover the data from the drive.
Yeah, I went to, so I have a MacBook and I went to Apple and they said they can't recover anything. I'm not even sure what happened because I was trying to recover the hard drive.
Yeah.
But yeah, they just weren't able to
Macs are
recover.
different, right? But they have an onboard hard drive. They don't have a separate spinning disk. So that's different.
Yeah.
Too bad.
Well, let's see. I don't see any more comments coming in. Ask in the chat channel.
One more question, Ria. In your presentation on the title slide, you had a couple of other names listed also, but they were from different high schools. So what was the nature of your collaboration with those other people?
So a lot of people from a lot of different high schools were admitted into the program, and we were placed in groups at random. So I was working with these two people, and that was pretty much it. I asked them if I could, present this, and they were okay with it. So yeah, that's pretty much it. We just collaborated on this project.
Right, but in terms of your actual research, were you
okay.
writing the code together, or like what exactly is the nature of the collaboration between the three of you?
Okay. Yeah, so I pretty much I wrote almost all of this code with some help from Shagun, and we got a lot of help from our mentor, who is a PhD student at UCSB, and the other partner, Richard, he wrote the code for the lines of best fit and he wrote, he basically did this entire part. He just defined it into functions, but all of the other part above me and Shogun wrote, and then we all worked on our paper together.
Cool.
Yeah. So did you actually have access to their telescopes, or were you just working off of the data that they provided you?
No, we actually had access. So it wasn't a telescope where you would like go there and observe. It was it was like a robotic telescope.
Yeah.
Yeah. So we could just like use their website and make just book observation slots. And yeah, that's basically what we use to make our observations.
Okay. All right. Thank you.
Let's give it a couple of more minutes if anyone wants to jump in with the last question.
Ria, if you join the astrophysics program in a university, some universities do have collaborations with many observatories, so you may actually get to go to one of those and use the telescopes there. My daughter did physics and astronomy at RIT, and she got to go to Kitt Peak Observatory in Arizona, and she spent almost like 5 days or 6 days there doing a lot of observing. So that was a really great experience for her. So I hope you get to do that as well.
Yeah, that's really cool. I'm actually, that's one of the things I'm looking forward to. That's why I kind of like the colleges that I applied to, I wanted to make sure that they have like observatories nearby, because I really want to get the hands-on experience, because like I like the online stuff, but I think the in-person stuff, like learning how to work a telescope and stuff is pretty cool.
It doesn't even have to be nearby, right? Because the school that my daughter went to, that was in upstate New York, but the observatory was here in Arizona. It was just a separate collaboration that they had, and a bunch of students got the opportunity to go there for a week and actually live on site and do some observations through their telescope. So that was a really good experience for her.
It sounds like a really cool program.
Yeah.
One more last thought coming in. If this star was HD 189733, it means someone studied 10x, 4x, 189733, 7 million stars before. Whoa. Okay. I didn't look at it that way, but yeah.
I'm not sure if they're numbered serially like that. They must be using some other
formula though, right?
Sorry?
There is some formula involved though, right?
Yeah, they must be using some other mechanism for naming these stars. It can't be just serially.
Well, which is star number one would be my question. Right? Like
probably the sun.
Very sure for that, probably. So that will be interesting to find out. So
yeah.
Stefano is saying AA0001.
No.
Okay, well, this was great. Thank you for doing this, Ria. I know it took us some time to get you on the calendar, but we made it happen. I'm happy about that.
Yeah, thank you so much for this.
Yep, and hope to see you in person whenever we are able to do that.
Yes, definitely.
At one of future SJAA events. And as I said in the beginning, if any of you, including Ria, is interested in helping us out with running SJAA, please reach out. We would love your help. Thank you so much. Have a good weekend, everyone. I'm going to end this streaming before I let you all go, to make sure it doesn't abruptly end for our